This is StarTalk. Neil deGrasse Tyson here, your personal astrophysicist. This is Sports Edition. And I got with me my co-host, one of two for this format, Chuck Nice. Chuck, how you doing, man?
Hey, man. Yeah, Sports Edition. I'm the guy who, in whatever iteration of sports, I'm the guy bringing the water.
Is that what you do? The Gatorade?
That's me. I'm the Gatorade guy.
Oh, no.
That's me. Hey, how you doing? You thirsty? You thirsty? You need some electrolytes there, buddy?
Maybe squirt it into your mouth?
Yeah, come here. Yeah, exactly.
We got Gary O'Reilly. Gary.
Hi, Neil.
From the UK. You're with us stateside now, I think. But
I am, yes.
Originally the UK. Played professional soccer there.
Yep.
For professional football, I guess they call it. And you were an announcer there. So we're delighted to have both of those features within you. So, Gary, just tell me what you got up your sleeve for today.
Something we take for granted, Neil. Imagine surfaces. We engage with so many every day. Smartphones, our clothing, footwear, kitchens, even paint. But what is happening at a molecular level?
Oh, they're all disgusting. That's what's happening at a molecular level. They're all nasty.
All right. Well, we'll see if that's the case. I mean, is it material science? Is it physics?
Wait, Chuck, I didn't know you had such strong opinions about molecules.
I do, especially when they form bonds that actually hurt me.
Oh, got it. Molecular bonds. Okay. Yeah. Go on, Gary.
All right. So, I mean, and then we'll get to the friction, which happens when certain surfaces connect. And then we have biomimicked so much from Mother Nature and tried to recreate her work. And we've even taken these inventions into space. So we'll go there as well. But really right now, what we need is someone who could make paint drying seem interesting. And I think what we have is just the person. So, Neil, if you would like to introduce our guest today, then we'll go from there.
Well, I'd be happy to. So we've got Laurie Winkless. Laurie, did I pronounce that correctly?
Perfectly, Neil. Yeah, well done.
Excellent. You're coming to us with an Irish accent, but at the moment you're in New Zealand. Very cool. Thank you for hanging with us, even though you're on the other side of the earth at some unholy time of day in this interview, because it's a regular time of day for us.
Oh, it's all good. It's almost 9 a.m. It's all good.
Oh, that's okay. Okay, 9 a.m. on tomorrow. Yeah,
tomorrow
for
in the
us.
future. Mm-hmm.
Yeah,
she's from the future. She's from the future.
You're rather sprite to be coming to us from the future.
It's much better here.
Early morning tomorrow. You have a background in physics and in space and in working in national labs. You're a science communicator, a lecturer. I love it all. You've got books. One of them is called, was it Science and the City? Is that one of your books?
Yeah, that was my first book.
I love it. A wonderful title. And most recently, what's called Sticky, The Secret Science of Surfaces. And that sounds all about friction. We've done several shows talking about friction in sports. So this will fit right into that portfolio. So let me just sort of start off. I think I got to start a question I got for you. So I think people want to know about gecko feet. Is this?
By the way, isn't that gecko from New Zealand?
There is a gecko in New Zealand, and it's a very unusual one because it lives in the mountains. It's an alpine gecko.
No, I was talking about the Geico gecko.
Oh, no, not him.
Oh, yeah. What accent does the Gecko
What
gecko
accent
have?
does the Geico gecko have?
He's in East London. You'll know this, Laurie. There's a soap opera in England called EastEnders. It's based in the East End of London.
We have
he is one of the cast members. Oh. And he's not putting on a voice. That's him.
That's him. That's just him.
Although he's not green.
Wait. The gecko isn't the actor who is that voice is a cast member.
Yes, not the gecko, no.
I'm sorry. I said last time I saw EastEnders, I don't remember talking animals.
I don't remember the gecko.
No.
Yeah, talking gecko would make it a lot more interesting.
All right, well, let's
All right,
Laurie, let's unravel the gecko. So if I've got this right, you've got hairs, on scales, on toes, on feet.
Yeah, that's pretty much it, actually, Gary. Yeah, the gecko foot is what we call a hierarchical structure. So what that really means is that it has features of different sizes that combine together to give the gecko its climbing superpower, I suppose. So if you look at a little gecko's toes, usually the toes themselves are pretty strong. So that's often enough to get them to cling on to like a bark of a tree or whatever.
But just to be clear, Laurie, I've never done this. You said, if you look at a gecko's toes.
You've never looked at a gecko's toes?
I'm sorry.
So,
yeah, I understand that there's a fetish site where you can do that.
No, I really hope not.
Yeah. Okay, go on, Laurie.
So I'll take a step back. Geckos usually have 4 legs. We'll start there. They're little lizards. And they have, depending on their species, like 4 or 5 toes on each foot. Okay. Right. So the thing about their toes is, and sometimes if you see them at maybe a zoo or something, if you see them on a glass surface, that's usually the best way to get a real like insight into what's going on. So you've got their little feet. On their toes are covered in these flaps of skin, and they're called lamellae. They're just stripes of skin. Yeah. And for the longest time, scientists, we just thought that it was to do with those flaps of skin. Like maybe they were acting as some sort of like a suction cup, or
they look
maybe
like a pad when they're pressed against a flat surface. They look kind of like a pad.
They flatten out. Yeah, they flatten out. So like that was what we thought. That was all we thought that geckos could do. But like as microscopes began to develop more and get better and better, and we could zoom in a bit further, like Gary said, we realized those flaps of skin are actually covered in this very, very dense forest of hairs. And they're called setae. So they're just hairs, but they increase the surface area so much. So it's now not a flat bit of skin, it's a really heavily textured forest of hairs. If you zoom in on the end of each of those hairs, you'll find that they each have like a really bad case of split ends, right? So each one of those hairs splays out into lots of other smaller hairs. And the ends of those hairs can make such intimate contact with surfaces. Now, when I mean intimate contact, I mean getting within 1 nanometer of the molecules that make up the surface.
Oh. So what you're saying is the surfaces we might think are smooth, but on the very small level, they're not. And so if you have something small enough to get in the nooks and the crannies, especially the crannies, then I don't know the difference between a nook and a cranny. Chuck, you have any insight into that?
Yeah, the nooks are not as delicious.
The crannies, okay.
But yeah, everything is rough. So what you really want to do is you want to increase the contact points as much as possible if you want to get to touch the surface as much as possible. So like when you will see geckos, and if you see them in the wild, they can climb on everything. They're running across waxy leaves, wet rocks. They can climb on glass. They can be inverted on sheets of glass, which are it's a material we think of as really smooth. Right. But yeah, as Neil said, on the microscale, it's not smooth. It's very rough and textured. So these tiny hairs can kind of get in there, and they can start, it's a force called van der Waals interaction. It's a force that you can only tap into when atoms are close enough together. And that is what the gecko uses. Like the gecko's foot is effectively feeling for electrons in the atoms of whatever the surface is that they're climbing on.
What you're kind of describing on an atomic level is Velcro.
Yeah. Yeah, to be honest, it's very similar. Although
it's basically
electric Velcro.
It's molecular Velcro with electrons and looking for a signal rather than just clasping together and pulling apart.
Yeah, and the thing that's even more impressive about the gecko's version of this Velcro is that it can detach really quickly. So when you're pulling pulling geckos apart, don't do that.
Yeah. That's my favorite. It's my favorite pastime, by the way, Laurie.
When you're pulling Velcro apart, you get that like really loud noise, and it takes quite a lot of force. But all a gecko needs to do is it curls its toes back, and that changes the angle that those split ends, those hairs, are making with the surface, and that turns off its stickiness instantly. So geckos can turn on and off their stickiness depending on the orientation of their toes.
Yeah, otherwise they wouldn't be able to actually walk.
Exactly.
You place them down and they just get stuck there forever.
Yeah.
Right.
Yeah, being ultra sticky isn't that useful, to be honest. Like you want to be able to turn it on when you need it and turn it off when you want to scarper. So yeah, the gecko has all of these features that are all working together to get that contact at the atomic level, at the really talking about electrons in order to climb. So, yeah, they're amazing little lizards.
Am I right here? Laurie, where you get a a gecko that may be a half a pound or a pound in weight, right? And you stick it to the ceiling, and then it can hold nearly 300 pounds of weight. Now, how? The question is broke down in two parts. A, how? And B, how on earth do you test that it can hold that much weight without being cruel to a gecko?
Unfortunately, there's a few geckos who gave their life for that experiment.
To be honest, if you look back at the early history of gecko research, there really are a lot of geckos that were treated badly. But in terms of this research, it's really based on a measurement taken on a single one of those hairs, and then they scale it up to, so it's kind of, that's why I say in theory, right? There's this kind of a scaling question, because, really a gecko shouldn't ever need to be able to support that sort of force. Why it's so good is because it's not usually in a lab, right? Like I said, it's usually running around in the forest.
I don't want the Geico company to learn about this, because they make TV commercials where that little gecko is saving people dangling off a cliff.
Oh no, we don't want that.
Right.
Actually, Neil, that's kind of cool.
All right, Laurie, so here we go.
Wait, before we,
go on.
I know we're going to get off of geckos in a minute, but I'm just fascinated because we're talking about sticky, so I know we got to leave the gecko. However, when you look at the design of their anatomy, is that also to disperse their weight so that they can do these things you're talking about? Because they seem
what
to
a
be
good question.
They're like super stretched out with a tiny little skinny body.
Totally. They absolutely do. The whole animal has a role to play. It's not just its toes. Like for a start, they kind of do jazz hands when they're trying to try to balance out the forces as much as possible.
For the non-dancers out there, jazz hands are fully open, palm forward, all fingers spread.
Indeed.
It's showtime, folks.
Showtime at the geckos. But on the ceiling, they'll do that so that their toes are pointing in opposite directions, so that the forces are all spread out evenly across all of their toes. And a gecko can very easily just cling with a single toe. They don't need all of their toes to be perfectly engaged in order to be able to climb.
That's just showing off.
I know, isn't it?
Okay, so now, once because it's taken us basically till the 21st century to really get a grip on understanding what's keeping a gecko glued to a wall or a ceiling.
I see what you did there, Gary, so get a grip on this. Yeah.
Thank you. And I know these things aren't just thrown together. We've mimicked that. And we came up, we being very smart people, not me, came up with gecko tape. And we have actually gone into space with things based on a gecko's feet.
What's gecko tape? What's gecko tape?
So
Laurie?
Gecko tape, it kind of came out of a lab at Stanford. And what they've done is they know that it's not possible. We do not have the ability to recreate the level of complex structure that a gecko has naturally evolved on its toes. But what they can do is they can kind of take some of the essential elements and kind of cheat a little bit, copy some of that. And what it looks like really, and I got to play with some myself when I visited, it's a silicone rubber, so a very flexible gray rubber. And if you look at it, it just looks quite rough. But if you look at it under a microscope, it's actually covered in tiny little wedges. So it's been patterned with these wedges that are angled. And they're at a similar angle to the setae, these hairs on a gecko's foot. So what they do is you can apply that, if you have that on, say, like a robotic arm for something, you can bring that robotic arm up against, say, a solar panel if you're on the International Space Station, and you put the gecko tape up against whatever it is you're trying to pick up, and you tug it down slightly. There's just a little button on the system that causes those wedges to splay out. So again, kind of tapping into the same idea as the hairs, although much, much larger than the hairs. They're not quite they don't make quite such intimate contact, but because the gecko is so special, it doesn't need to make quite such intimate contact. It can make a little bit of it, and it does enough. So you can do that without using like a suction cup, which is usually how we move big awkward things around. You can do it without using any electricity. There's a lot of grippers that we use electricity, electrostatics to pick stuff up, and they don't have any clamping forces. You can actually pick up very delicate things just by putting this gecko tape, the silicone rubber, onto the surface and causing its wedges to kind of splay out and move
Forgive
around.
me, but the first thing I thought of when you were describing this tape is a new arcade machine where you want to get the toy inside the thing. You just, because you can never get it, right? You never get the toy. With the clamp, we get some of your tape, we win all the toys.
Every time.
Oh, yeah.
Every time, yeah.
All the toys are coming
absolutely.
home with me. Okay. This is amazing.
Yeah.
Yeah.
So this is actually used in space now?
Yeah, so it was trialed initially on the Vomit Comet, and then it eventually went up on the International Space Station. I think it's had several trials now on the International Space Station to be used as a low gravity gripper and manipulator. And
Wait,
it's
could you
already
please tell the 1 in 100 of our listeners, because that's all it will be, what the Vomit Comet is?
Oh, yeah. So the Vomit Comet is one of NASA's test facilities. It's a plane basically that flies in a parabolic path, and it simulates, low gravity for short periods of time. So if you want to test something out in low gravity, that's a good way to do it. So
or even zero gravity, right?
Or zero gravity, yeah, indeed.
Yeah.
If only, I'd love to have a go in the Vomit Comet if anyone's listening.
I'll put in a good word for you.
Thanks, Neil. Thanks.
With Dramamine.
But yeah, so it is being used, and it's actually already being developed and used on factories on Earth as well. So they've commercialized some of these grippers to be used in robotic systems to pick up awkwardly shaped objects.
Yeah. Wow.
Yeah. It's pretty cool.
That's more than cool.
So tell me about the what happens if water is between your thing and the surface?
Yeah.
Usually because water is like the enemy of tape, right?
Yeah.
Yes.
If you get tape wet, nothing sticks anyway, no how.
Yeah.
So what goes on there?
Except for Flex Seal tape, I have to tell you. I've seen those.
It's good stuff.
Yeah. Sorry.
Yeah, water is a problem. You're right, Neil. The gecko has evolved to cope with it because its feet, as well as being amazing for gripping, they're also hydrophobic. So those feet actively repel water. They push water out of the way so that they can make effectively dry contact with whatever surface it's touching. For the silicone tape, again, silicone itself is hydrophobic, so it tries to repel water as much as possible. It's not perfect, but it works.
So
well
let me
enough.
ask you this. Is there any way to take this type of technology and apply it to tires? Because I could see so many applications for a safety. As a matter of fact, there was a show called Speed Racer when I was a kid, and
I remember Speed Racer.
You remember Speed Racer? So
You're going to sing
Racer
again,
had-
aren't you? You're going to sing. The pair of you are going to sing, aren't you?
Oh my God! Don't make me! Don't make
Hey,
Here
comes Speed
here comes
Racer.
Speed Racer.
He's a demon on wheels.
Okay. Anyway, one of the things were these super sticky tires that would allow the car to ride on any surface and even stick to the walls. And of course, that can't happen. But
Or to not lose traction on a
not
wet
to
track.
lose traction on a
Right,
wet
because
track.
they actually stop NASCAR when it rains.
Yeah.
And if you,
All right, but we're going to do tires in the next segment.
Okay, well, then
Okay. Well, let's just do that. Wait. Hold on to that. But put a pin in that.
Yep.
And Laurie, you can hang out. We got 2 more segments with you, and this is just amazing. I mean, I want to do the whole thing on geckos, but
I do
know we got other topics.
Who knew? Who knew?
I have never been so into geckos in my entire
Me
life.
neither. It's
And
like,
they come in
damn.
different colors and different sizes.
Yeah, they're adorable. They're wonderful little lizards.
Damn. Okay, when we come back, more StarTalk Sports Edition with surface expert Laurie Winkless. We're back, StarTalk Sports Edition. We spent an entire segment talking about gecko toes. But as interesting as that is to a naturalist, this is Sports Edition, damn it. And I want to know, how are we going to put gecko feet on rubber for cars and stuff, car races? Can we go there, Gary? Is that
We
someplace
can
you
go
take me?
anywhere we want. We've got gecko feet
Okay.
and wheels.
Let's lay down the rubber on that. We got Laurie Winkless, who's an expert on gecko feet.
I know.
Laurie, is
Okay.
that on your business card? You know,
No, definitely not.
What do you carry around on your business card? Oh my gosh! But anyway, I'm delighted you're coming to us from New Zealand. Beautiful countryside. I'm not the first nor the last to say that. And thank you for coming on the line with us here across the ocean in
My pleasure.
North America. Yeah. So Gary, take it
All
over.
right, so here's something that may or may not be in people's thinking, but it's a wiki fact. Tribology. I'd never heard of it before, but it is the science and engineering of interacting surfaces in relative motion. It includes the study and application of the principles of friction. Now, I hadn't thought of that as a science, but tribology is what we have here in
Why don't they call it
discussion.
frictionology or something? Why they got to be obscure about it?
Because the ancient Greeks got there first, and they've decided it's tribology.
All right.
That's true.
Slickology would be better.
There you go.
So have you ever heard of that, Laurie? Tribology?
Yeah. So a lot of this book is about tribology. The short version is like it's the science of rubbing and scrubbing. That's how it's often described.
I love it.
Which I love. Yeah.
I gotta tell you, that sounded a little sexual there, Laurie. That's all.
Yeah,
I'm
well, I
saying.
mean, there's an entire chapters on lubrication as well, Chuck. So yeah, there's plenty of opportunity for innuendo.
All right.
All right. None of this is making the show. All right.
What we've known, and we've had shows on this very topic, is that professional auto racing often, in fact, I might say all the time, leads automotive technologies with innovations that ultimately filter their way back to commercial vehicles. But we look at the tires, as far as I see all the rest of the technology, they're still using rubber tires on the track.
Right.
Am I missing something there? What's either NASCAR or especially Formula One, where the full rubber tire is sticking out all bare? What's
When
the
are we
latest
getting
on
Gecko? When are we getting Gecko feet on our Formula One cars? And listen, if you think about it, when you look at racing slicks, okay, they're kind of they've got to be a significant weight factor to the car, So maybe that's something. If you want to lighten the load, Gecko feet tires would be a great way to do it.
Yeah, I mean, it's a funny one. The main problem with Gecko tape is that it's not very robust. So it's not actually very good. It wouldn't be very good under the weight of like a Formula One car or even just the Formula One tire, like you said. But I should say that they use rubber because it also, if it's designed well enough and if the track is smooth enough, it also can tap into those same forces, the van der Waals forces, because like those big Formula One slick tires, they can make a similar intimate contact with a racetrack that a Gecko can make with a wall. Like racetracks,
because they're soft at some level, right? I mean, that's why they're called rubber, right? I mean, they fill in any little microscopic gaps.
Yeah, exactly. Like
what's up, baby? This is your tire. How you doing? Just trying to make a little intimate contact.
Formula One.
Sorry,
after
Laurie.
hours. Yes. Okay. Fine. Okay.
But so, Laurie, so when you've got a Formula One race car, and I mean, people like Lewis Hamilton will hammer the pedal down, and this thing's gone over 200 miles per hour.
Yeah.
Plus, with a Formula One racetrack, you've got all sorts of curves, bends. I mean, a tyre will go through all of these different forces, deformation, torque, all the rest of it. How are you ensuring that it's still able to tap into those van der Waals forces under all these distresses?
Yeah, really good question. There's two main ways that a tire makes contact with the road. And one of them is the way that normal tires make contact with the road, which is kind of what Neil said. It's about the rubber. Rubber is this material it's a viscoelastic material. So it's something a bit like a very viscous or sticky fluid and an elastic solid. So it kind of sits somewhere in that range. And what it means is that tire rubber flows into all of those bumps and crevices and all of the roughness on a racetrack. And as it flows, it makes a kind of a frictional interaction. And that is mostly how tires work. That's mostly how like road tires will grip to the road. Right. But Formula One tires are usually flat, very, very particular compounds of rubber, like particularly their stickiness, their viscosity has been very well defined. And they're huge, right? This massive surface area that makes contact with the track. The track is usually also very smooth. So it can also tap into that van der Waals interaction, assuming the rubber can actually just flow properly into the track. Now, sometimes you'll see a Formula One driver and they talk about this. They talk about this in other motorsport too, about laying down some rubber, right? This idea of actually like the tire degrading intentionally. Formula One is totally based on that. Those tires are designed to degrade. They're designed to leave tiny, thin layers of rubber on the track because that increases the grip for the next time you go around the track. You lay down the rubber to increase the friction between your tire the next time you pass by. But like on a normal car, you do not want your rubber to be degrading over the course of a few kilometers, right?
Yeah, because they change their wheels in an F1, you know.
Exactly.
Yeah.
And
every
Formula
race,
One tires, like the cost, I don't even know how much it would cost.
Yeah, you don't want to have to change your wheels on the way to, you know, to the 7-Eleven, you know.
No.
You know what,
Yes.
Chuck? You know, when you're talking about you want Gecko tires, right? Gecko feet on a tire. Have they, Laurie, done exactly that? Because a Formula One race will take place in the rain, and they'll obviously then have a tread pattern on the tire, which then disperses an awful lot of surface water. So are they using a similar sort of technique that a Gecko would for being hydrophobic?
Wait, Gary, do they swap out the tires when it rains?
Yes, they do.
Okay, got it.
It's a different tire with a.
Oh, they'll have a whole team
normally with a channel through the middle of the tire, and then some kind of some type of channeling that moves the water away.
Okay.
Neil,
Exactly,
they'll have a whole team to manage to manage the tire, to manage the setup of the car based on the weather. It could be humidity, temperature.
I think they should have it also
precipitation.
in snow, just to.
Yeah. Well, that's if you watch like if you watch rally, they're racing on ice, which is just crazy.
I know, but they don't have tire changes, do they? In rallycross,
No, exactly. In
But
rallycross,
Formula
right.
One, you can. But
Yeah,
are
you
they
have the
able
luxury
to
of that.
push that super hydrophobic sort of setup?
They do. The rubber itself is a bit hydrophobic. It does repel water, but really it's the design of those tread patterns that pushes the water out of the way. So like a Formula One, I think it's the 2020 Formula One tires. I need to check, but they can remove about 65 liters of water per second when the car is moving at full speed. Like every single pattern on a tread has been designed to suck the water up and, like Chuck said, kind of push it out the sides of the tire so that the contact is as dry as they can possibly get it. Like there's a limit, right? There's a limit as
so
to
the
how much
tire is basically a windshield wiper for the road.
Yeah, exactly. A very expensive windshield wiper.
Expensive windshield wiper.
Yeah.
So my question then is, from a material standpoint, why not just do two things? One, increase the friction of the surface upon which you're driving, and two, make it so that the tire becomes more interactive with that frictioned surface, or that surface that has more friction.
So, Laurie, let me tighten up Chuck's question.
Please.
Okay. If the whole point is to have rubber grip into the texture of the track, why not actually chew up the track?
Yeah.
So that the rubber is getting so in there, it's not even about friction. It's actually pushing off of vertical walls that have been cut into the track as you go around.
Yeah, I think the argument really is about, you want to keep this a fast sport, right? And friction, you need some of it in order to, get the traction on the road to propel yourself forward. So you do need some friction. But if it's too high, then your car has a much lower maximum speed, right? It reduces how fast your car can go. So you've got this, and it's
So this is
friction,
the point
it's
of
always
equilibrium. You got to find that balance point.
Okay.
Yeah, there's always a balance. There's always a compromise. Like you need some, but not too much. And then if you're looking at like an ice sport, like skiing or something like that, you're looking at trying to minimize friction. But it's always, you do need some, but just not everything. Because if you have too much friction, things just grind to a halt.
Laurie, about 50 years ago, Formula One stumbled across a thing called carbon, if I'm not mistaken. And since then, it's been part of the space shuttle. What's the connection?
Yeah, carbon is one of the materials that's used a lot in Formula One because it's very, very strong and it's very, very light. And it's in Formula One's context, it's used in brakes. So it's used as a lightweight way to produce a strong surface that you can interact with. And as with most things, they find applications elsewhere. I don't actually know which one came first in terms of carbon, whether it was developed specifically for Formula One or whether it came about as a byproduct of another industry. But yeah, it is very important material now.
Wait, Laurie, forgive me, but can we be a little more explicit than just saying carbon? Could you tell me what the hell that is?
I've heard of Duran and
no, fair point.
And New York.
New York. Saatchi and Saatchi.
No, that's fair point. So if you've heard of carbon fiber, you might have heard of that. It's carbon, it's like long strands of carbon fiber arranged in some sort of matrix, some sort of polymer. But carbon is those carbon fibers that have been arranged in a matrix of graphite. So the actual matrix itself is carbon, but just little flakes of carbon. And then the fibers going through it are these very aligned carbon fibers. So it is carbon and carbon in two different forms.
So two different forms of carbon. Got it. Okay.
Mm-hmm. Yeah.
So if you threw in diamond, you'd have carbon.
Yeah, exactly.
I'm just checking.
Carbon cubes.
And then as we found in the universe, as well as in the lab, there's buckyballs, right? Mm-hmm. Carbon-60, another form of carbon. So just throw it all in there. Get carbon.
Exactly. Formula One has the money for it, surely.
Yeah, they sure do.
But they use that money to do something that I think a lot of people have been hoping to do for a long time when they got a KERS system, the kinetic energy recovery system. And how advanced was their thinking to be able to bring that forward for motorsport? But we haven't seen it in the general public transport, have we?
You see a version of it.
Well, I have a regenerative braking. Is that the same thing?
Yeah, I was going to say that's a version of it. Regenerative
it's the same thing. Yeah. It is the same thing. So once we started putting electric motors into our cars, that becomes something that's a really useful form of energy to capture.
Capture and return to the electric motor.
Mm-hmm. So what does it hand it to a flywheel or something, or is it in what form is it recaptured as?
And by the way, you should probably explain the whole concept because clearly we're all familiar, and I feel like we're a little inside baseball right now.
So it's like
Chuck, we're inside friction, not inside baseball. Yeah.
Well played, sir. Well played.
Okay.
So the regenerative braking is effectively when you put the brake on, you effectively turn your motor into a generator. So you flip around its behavior. So it generates electricity. In a Formula One car, I believe it is just used in terms of electricity. It is just captured and used elsewhere in the car, but I'm actually not sure. So I won't pretend I know.
Wait, just to be clear, you said when you put the brake on, let me clarify that. Mm-hmm. What you mean is when you press the brake pedal, brake pads are not touching your wheel. What's happening is the forward motion of your car is getting sucked away back into... Isn't that what's happening?
That's it. Yep. Yeah. That's it. And
So
it's brilliant.
Your kinetic energy is getting absorbed without even using friction in that sense.
Yeah, because usually brakes are just about slamming on the friction as high as possible.
Right.
Flintstone feet.
That's
what they are.
Do they have Flintstones in New Zealand? I don't know. That's just
I remember them as a kid, though. Yeah, I definitely watched the Flintstones.
Flintstones. Yeah. That's the accelerator pedal and the brakes.
Yeah.
Is Fred Flintstone's big old three-toed feet. They have 4 fingers and 3 toes. That disturbed me more than the fact that they're living in the Stone Age with...
Do you know that this is the first time that I have heard that? And you're right. I'm picturing...
You never noticed that?
I never noticed
that.
Oh my gosh!
I
think at least give the man 4 toes to match his 4 fingers.
4 fingers.
Isn't there something about when the animator draws a hand with 4 fingers and a thumb, it looks wrong, and so that's why they take away 1 digit. Apparently.
Okay, so Gary, 4 fingers never looked right to me. Okay, ever, and especially not the 3 toes with his big old caveman feet. So, no.
But they make
we
great
gotta
brakes.
take a break. We're
They're
talking about
great for
friction.
regenerative recovery.
We're talking about friction. We're talking about Formula One. We got rubber. We got gecko feet, all in one freaking conversation. Go figure. And at the center of all that is Laurie Winkless. We'll be right back. We're back. StarTalk Sports Edition. Everything friction and surfaces with one of the world's greatest exponents of this subject that I have ever seen, Laurie Winkless, who's coming to us from New Zealand. Laurie, thanks for being on StarTalk and illuminating us with all of your surface wisdom.
My pleasure.
So when someone says, it's only skin deep, you're saying, yeah,
Exactly.
that's where the action is. Okay.
Exactly.
So we've talked about what you've learned sort of scientifically from Mother Nature. And at the end of the day, stuff only really happens if people can make money off of it. If there's sort of product development, applications that can improve what we already have or invent something new that we never thought we needed. So do you have some good examples of that, maybe?
Yeah, I'll give you one that it's still, I would say, at the research end of the R&D scale, but is pretty exciting. And if it works, it could give us boats that never get wet, which I think is pretty cool.
Boats that never get wet.
They never get wet. No. So
Wow.
That's like Charlie in the Chocolate Factory, square sweets that look round.
yeah, exactly.
Yeah.
Precisely, Gary. Yeah.
Okay.
Yeah.
So wait a minute. Let me just put this out. I mean, let me think this through. If the boat never gets wet, but it's moving through water, then that's about as frictionless as you could ever get.
Yes, it's just moving through air at that
Super
point.
fast boats.
Is that
Yeah.
right?
Yeah. And you've got, if you think about the fact that like 90% of the world's trade happens by sea,
Right.
if we could reduce the friction that those massive container ships experience as they move through the water, you reduce the amount of fuel they use. You improve the environmental, properties of that. So that is like something that a lot of different technologies are attempting to do. You can already get boats that, have a low friction coating on them. But one of the things that I came across and I thought was really cool is there's this fern. It's called a Salvinia fern, and it's usually like an invasive species. It forms these massive mats on the surface of waterways, so it can often cause damage to anything living in the waterway. But the cool thing about it is that it is incredibly hydrophobic. So if you've heard of the lotus effect, which is this idea that the lotus is always pristine, water, nothing sticks to it, nothing ever, dirt doesn't touch it. It's kind of like that, but way better. It's way more impressive. And when scientists started to study what it is that makes this plant so good at repelling water, they started by looking at the surface. So in a way, it's kind of gecko-like. It's covered in loads and loads of hairs. And each one of those hairs is shaped a bit like a whisk, right? So it's kind of got it breaks into four points that join at the top. The whole leaf and all of these hairs are covered in a waxy surface, which makes it water repellent. But the cool thing is the very tip of that whisk is not water repellent. It's water attracting. It's hydrophilic. It attracts water. So what that means is that you trap a layer of air. The leaf traps a layer of air in its hairs. And because water is pinned onto the top of each one of those hairs, the air can't get out and the water can't penetrate in. So you have this permanent layer of air that the leaf has around itself.
You're really explaining kind of a microscopic hydrofoil.
Yeah, well, this is where when the botanists kind of realized that this is what's going on, they managed to recreate it. They managed to kind of produce coatings that have a similar structure, this combination of hydrophobic, so water repellent, and hydrophilic, water attracting, and capturing this band of air. So what they want to do is develop a coating that you could apply to a boat that retains a layer of air around it permanently, a stable layer of air. And there are some boats boats that have these, they produce bubbles. Like there's an actual system that spurts out bubbles around the edge of a boat to try and reduce the friction in a similar way, but it's just not as stable as something that would be, you know, a solid layer of air.
Wait, Laurie, I thought I remembered was it a TV commercial? I might have been, you know, YouTube surfing, I think I was. And I came across, it was like a container of mayonnaise and a container of ketchup.
Yes!
Two famously bottle-sticking substances.
Yeah.
And they just tipped over the mayonnaise, and all the mayonnaise just came right out of the container.
Yes.
And they tipped the ketchup bottle, and all the ketchup just came. Nobody was shaking it or pounding it or squeezing it. Did it have one of these surfaces that you're talking about?
No, it's actually got another surface that's called, it's called slips. There's so many, honestly,
There's
guys.
so many
That's out of control. Oh my God.
We're filthy with surfaces.
You see now why I had to write a whole book about them, because they're just amazing. So that's a different material actually, and what it does is it basically they put a coating that's porous, so it's got loads of holes in it, but then those holes are filled with water, so it's kind of using water to stop other liquids from sticking to it. So they've textured it in a way that it traps its own little layer of water, so that the ketchup then just falls out of the mayonnaise.
Just to show you how biased we are, just as members of civilization, I'm looking at that demo and I'm thinking, what's wrong with the ketchup?
Exactly.
So, you know, I'm not eating that ketchup.
Yeah, I'm not
thinking
either.
It's a ketchup issue, not a surface issue. That's what I'm thinking to myself.
Because
it does look a bit creepy.
It looks creepy. It looks creepy.
Ketchup ain't supposed to. God made ketchup to stick to the inside of the bottle.
Right. Exactly. That's like seeing peanut butter slide out of a jar.
That's wrong.
If you ever saw peanut butter slide out of anything,
Walk the other direction. Run. Walk. Don't run. Run. Don't walk away from that.
Peanut butter is sentient. Okay.
No, totally. It is quite disconcerting, I have to say. Yeah.
Well, what about when you talk about your surfaces that slip and slide? Mm-hmm. Is there anything that can make something more aerodynamic? Like you put a coating on a football, and now, instead of being able to throw it 30 yards, I can throw it 50 yards or kick it more importantly.
Yeah, good point. And actually, that's kind of where like golf balls came from as well, because the original golf balls were smooth, and they were made from basically they pack a ball of leather with these feathers, make it really, really hard, smooth surface. But they realized that the ball would travel further when it had been dinged up a bit, so when it had some like dents in it. So there was a scientist who designed a pattern, which is now what we know as a golf ball pattern, this dimpled pattern, and that reduces the drag on a golf ball by playing with the way that the air flows around it, and the formation of these little vortexes, these little areas of low pressure. That dimple pattern kind of plays around with turbulence in a way to reduce drag. So like a dimpled ball will travel about twice as far as a smooth golf ball of the same dimensions.
So it's really traveling in its own pocket of low friction air. Is that a fair way to say that?
Yeah, like everything moving through the air has a layer of kind of stuck air molecules right on its surface. And as you get further away from the surface, the air moves more and more and more.
Air sticks to me all the time. I try to...
Exactly. It's a pain. It's so sticky. You just don't even
Who's
realize.
ever thinking that way?
So, Laurie, is that the sort of thing that's going on with an aircraft, say, that was flying at 30,000 feet? The air temperature outside is minus something silly.
Yeah,
right?
yeah.
And yet
40 below.
And yet there's an issue for overheating. What are we experiencing with that?
Yeah, it's exactly that. It's skin friction. So it's effectively the air molecules bashing into other air molecules that are stuck onto the surface of the aircraft. And even though it depends on the altitude, of course, but the density of air can be lower than it is on the surface of the Earth, there's still plenty of air molecules to bash into one another. So the moving
especially
through
at 500 miles an hour, right?
Yeah, exactly. Moving through the air at high speed, you are causing massive transfers of kinetic energy. You are bashing air molecules out of the way like crazy, and in that process, you lose some of that kinetic energy. Transforms into heat energy, transforms into the high temperatures on the surface. So like a lot of the very, very high speed aircrafts and like re-entry vehicles, they've been designed, they're their surface chemistry has been really particularly designed to be able to cope with that happening on their surface. That's why, heat shields are so important.
I mean, we've discussed surfaces contacting each other, but we haven't discussed how we as humans interact with surfaces, particularly through our own skin. What happens at a molecular level when we are touching and feeling surfaces?
And how do I become Spider-Man with my own form of gecko feet?
Well, yeah, there's a dude, I think it's at San Diego University, Chuck, who could sort you out. He developed a climber based on the gecko tape. So he managed to scale a building, well, a few stories of a building on his own gecko. Yeah,
but it is true, however, there are some things, sometimes, I don't know, it depends on how oily or not your skin is. There could be something on the ground and you just touch it and it stick, like a playing card maybe will stick to your finger. Sometimes a penny might stick to your finger.
Yeah.
Some light little things will stick to your finger, but I don't want to claim gecko powers. So what's going on with that when that happens?
It's basically that we're a bit damp. Humans have this constant.
I thought it was going to be a deep explanation, Laurie.
No, unfortunately not.
We're just a bit, that we're sweaty.
Yeah, we just have water on us, and usually that's enough you get effectively a capillary force. The water that we are producing water all the time. We respire, so we are constantly covered in a little very thin layer of water, and sometimes that means that we can, stick a spoon to our nose, or we can pick up a piece of paper just by touching it.
Oh, I thought it was the vaccine that made that happen.
No.
Sticking things to your
thought it was the vaccine. Just like, got vaccinated. Look at me, I'm magnetic now. I don't know who's going to fix this.
So, Laurie, before we have to let you go, sadly, we're thrilled by the gecko. I think we all have. Are there any
Laurie,
other...
can you join the show? Can you be another...
no problem. Anytime.
Are there any other species out there that are kind of like owning it, like the gecko?
Yes.
Ooh, go on.
Sharks.
What?
Sharks are...
Furry, cuddly sharks.
Sharks. They are just perfect.
Okay, but wait a minute. Why would a shark need to grip anything?
Oh, we're just talking about surfaces.
It's the opposite.
How they move through the water.
Who owns their surface? Yes.
Yeah, there you go.
Keep going, Laurie.
I'm still stuck on gecko, but
no,
I
don't blame
now.
you.
I see what you did there. Stuck on gecko. Yes.
Yay.
Okay. Go on, Laurie.
Yeah, no, sharks
don't mind Chuck. Just ignore him. Go.
Sharks are incredible. If you look at their skin, and you don't even have to have a particularly fancy microscope. Don't do this to a living shark, right? I'm talking about like a museum, right? Don't touch a shark. But their skin is covered in these features called dermal denticles. And they're like very tiny scales. They're kind of like scales, but they're actually 3D. They're a real structure. And what scientists have realized is that we kind of knew that the shape and the placement of those denticles all over a shark's body must have something to do with reducing drag. It must have something to do with making it easier for them to move through the water. But what scientists realized in more recent years is that what's happening with these dermal denticles is that on some parts of a shark's body, it's the flow of water around this denticle actually behaves in a way as if it's gone in reverse. So it's as if the water is actually pushing the shark forward. It's not just reducing drag, it's actively helping the shark to accelerate through the water.
So the shark is drafting itself.
Yeah.
That is unbelievable.
Yeah.
Okay, but wait a minute. But Laurie,
Yeah.
let's bring in some evolution here because I got a question. I can't claim to have hung out with sharks. Okay, so I don't know of what I speak, but I don't picture sharks in high pursuit of their prey. Mm-hmm. I picture them stalking their prey.
Yeah.
All right, and so why would speed have been selected for in their skin water surfaces if that's not really what they're doing?
Very good point. I think the idea around it now is that these denticles have a different role to play on different parts of the body. So they're different sizes and shapes depending on, and they differ between species of sharks as well. So some sharks are they're more about speed, they're more about reducing drag. But in terms of increasing speed and reducing drag, really what that does is it decreases the amount of energy a shark needs to use to push its way through the water.
And importantly, because sharks have to move in order to breathe, you would want that to you would like that to be as easy as possible.
Yeah.
Because when you do need to go hunt, you haven't used up all
Okay.
your energy swimming around so you can breathe.
I'll give that, because I just know that if sharks were fast moving, chase you down to meet predators, then you couldn't have that slow cello in Jaws. Dun, 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 dun. You know, that is it a cello or a bass?
Remember? Yeah.
It's a cello. So whichever it is, it's like that's not the music you hear of something rapidly chasing something else.
No.
So it all worked out. It all worked out for the movie.
Yeah.
And by the way, we're going to need a bigger boat.
Thank you, Chuck. I thought you were above that, Chuck. I got the lowest hanging fruit. That fruit was already on the ground.
If you ever mention Jaws, I have to say that. I can't. I have to. It's a law.
So, Laurie, I think we gotta close this out. Do you have a social media we can track you down on?
Yeah, I'm on Twitter like way too much. So I'm at Laurie_Winkless.
And your books, tell me the titles again. They were so great.
Oh, yeah. So Sticky is just out. It's literally just came out a month ago in the US. So Sticky, The Secret Science of Surfaces. And my older book is Science and the City. And that's all about how cities work and what happens in the metropolis.
This is beautiful. I love it. I love it. And what are you working on now? What can we in the future? Because we totally want to bring you back. So give us an excuse to bring you back.
Thank you.
So,
well, what I'm working on right now is an article on chocolate making, physics of chocolate making, which is something I'm finding quite interesting. But I've no.
Okay, can we book you tomorrow? I
have to learn about it yet.
By the way, can we do some research for you?
Yeah.
Yeah, I'll send you some samples.
Okay.
But yeah, nothing else immediate. No more books in the immediate pipeline. Anyway, take a break for a little while.
We got to end it there.
All
so, Gary, Chuck, always good to have you doing this.
Pleasure.
All right, and Laurie, it's been a delight to have you on this program. We learned so much about stuff we didn't even know there was something to learn about. So that's always a good day, at least for me, and I'm sure for
Thanks,
Chuck
guys.
and Gary.
It was super fun. I listened to the show, so it was really fun to be
Oh, you
on.
do? Okay. Well,
Yeah.
thanks. You're a fan. Excellent. So I hope we lived up to your expectations.
Very much.
You certainly exceeded ours. So,
Thank you.
all right, this has been StarTalk Sports Edition. Neil deGrasse Tyson, as always, bidding you to keep looking up.